Sir, Madhivanan, sir.
Yes, sir. Yes, sir.
You can start now, sir.
Yes, sir. Thank you, sir. Thank you, sir.
Basara, sir, are you there? Basara, sir.
Yes, sir, I am there.
Sir, we will start now, sir.
Yeah, okay. Okay, sir. Go ahead,
Okay.
sir.
Thank you, sir. Good morning to one and all present here. I welcome all the participants to this Phase 4 6 days short-term training program on nanotechnology and functional materials. Now we are going to start sixth day and first session. Once again, thank you for joining with us. Now let me introduce our resource person, Dr. Basavaraja S. Toshniwal Brothers Private Limited, Bangalore. He has completed He has completed doctoral degree in 2003 from Gulbarga University, Karnataka. After his doctoral degree, he had joined Icon Analytical Equipment Private Limited and deputed at prestigious Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, as an application specialist to look after India Nanotechnology Laboratory from 2008 to 2013. This central facility was equipped with atomic force microscope, optical and stylus profiler. He got all the level of training on atomic force microscope and surface profiler from Bruker, formerly it is Vico, Bruker for Systems, Oxford, and KLA at Singapore, Beijing, and South Korea. He is well versed with all the advanced modes of atomic force microscope and profilers. We welcome you, sir. We are honored with your presence, sir. The current session topic is recent advances in atomic force microscopy by Oxford Instruments. Now I request our resource person to continue with the session. Requesting, sir.
Thank you, Dr. Rajesh, sir, for the kind introduction. I will present my screen now. Share my screen. I hope my screen is visible to everyone.
Yes, sir. Yes, sir. Visible. Perfect, sir. Perfect.
Yes, okay.
One more thing, you go to hide, sir. That
Sorry, sir.
hide that.
Hide. Okay, okay.
Yes, yes, sir. Yes, sir. Yes, sir. Good, sir. Good, sir.
Okay. Thank you, Dr. Chandrasekhar Reddy, sir, for inviting me and for giving opportunity to present our instrument in this AICTE sponsored webinar series. So in this, actually this presentation I have prepared mainly for the students or people who don't know much about atomic force microscopy. Okay, so before going to my talk, so just I want to briefly introduce about our company. So actually we are into microscopy and characterization instrument divisions, and we are headquartered in Bangalore, and we have regional offices in all major cities, and we are around 40 plus people working in our company. And coming to AFM, actually we have around 30 plus installations in India for Oxford AFMs. And other than this Oxford Asylum Research AFMs, we also deal with many other instruments from different principles. So coming to this talk, like in this talk, I am going to cover some basics of AFM and how to prepare the samples for AFM, and a little bit about our Oxford AFMs. Actually, this was Asylum Research AFM, and Oxford some 4-5 years back they acquired Asylum Research. So now it's we call it as Oxford Asylum Research AFM or Oxford AFM. So just briefly I will talk about it, and then I will talk about like how actually our AFMs are different compared to the traditional AFMs available in market, and I'm going to cover few application modes of AFMs in this talk. So okay, so coming to like basics of microscope, if you see in the market, there are different types of microscopies are available in the labs. So like if you divide them like into based on like what is interacting with your sample to get an image. So like we can mainly divide into three like that. If your sample is interacting with a light or photons and then getting an image, then that's called optical microscope. And if your sample is interacting with an electrons, then we call it the electron microscopes, like scanning electron microscopy, or TEM, transmission electron microscopes and all. And if your sample is interacting with a very sharp physical tip, and then getting an image, means then we call it as atomic force microscopes. Okay. So, like, what is atomic scanning probe microscopy? Is scanning probe microscopy is actually a family of technique where you use scanners and the probes. All those techniques comes under the scanning probe microscope family. So let's see, like, first, what is the principle of the scanning probe microscopy? So in the principle is like a very sharp. So this radius of this tip is around like few nanometers. So this will be very close to the sample. It may be touching, or it may be very close to the sample, and then doing raster scanning. Raster scanning means line by line scanning on the surface it is doing. So then this tip will be interacting with your sample. So the interaction between the tip and sample are very important to get an image. And there are different types of interactions will be there between the tip and sample. So based on that interactions, those techniques are divided actually. Like for example, if the tip and sample interactions are forces, means that is we call it as atomic force microscope. If your tip and sample interaction is a tunneling current, then we call it as a scanning tunneling microscopy. The same way, like if the interaction between the tip and sample is like ionic current, then we call it as a scanning ion conductance microscopy. And like if it is interaction is like light, then we call it as a near field scanning optical microscopy. So these are all techniques comes under the scanning probe microscope family, because in all these things we use like very sharp tip or probe, and then we use scanners for the movement. So these all techniques comes under this family. Okay, so the principle is almost same as I mentioned. Like so, tip and sample based on this tip and sample interactions, we will be getting a 3D image, and it is doing a like raster scanning. So, like coming to the like history of this AFM. So, in 1982, these people invented scanning tunneling microscopy, and they got a Nobel Prize in 1986 for this invention, scanning tunneling microscopy. As I mentioned in earlier slide, scanning the tip and sample interactions for HTM is tunneling current. So tunneling current, we get it only on the samples, like if your sample is conducting samples or semiconducting samples, then only we get some current. So you can't do imaging of insulating samples with the HTM. So that was the main drawback of this HTM. So we can do only imaging of conducting or semiconducting samples only with HTM. So that's why like later, so these people invented in 1986 the atomic force microscopy. Here in this case, like tip and sample interactions are forces. So those forces will be there on all type of samples, whether it's conducting or insulating. So we can do imaging of all type of samples, whether it is conducting or non-conducting. So, like now, in the case of AFM, like as I told, the tip and sample interactions are forces. Like if you take any surface, there are different types of forces will be available on the top of the surface. Like in that one, like if you divide, you can divide them into like two, like based on like how large these forces are. Like if those forces are very short range, means just a little bit above the surface, means then we call it as short range. If it is available up to like long range, then we call it as a long range forces. And these long range forces, like for example, if your sample is magnetic, so then magnetic forces will be there. And those magnetic forces are like depends on your how strong your magnet is. So based on that one, those forces may go up to like 100 nanometer or 200 nanometer, based on this like how strong your magnet is. So that's why like those we call as the short, long range forces. Like there are some forces are there, like for example this repulsive forces. These repulsive forces will be there above the surface up to like 1 or 2 angstroms only. Those repulsive forces are because of the electronic cloud of the atoms. Hmm? So there will be on top surface these atoms will be there. No? So the electronic clouds of those atoms, because of that one, there will be some repulsive force will be there above the surface up to like 1 or 2 angstroms only. Those we call as a contact forces or repulsive forces. Above that one, there will be some van der Waals force also will be there. Those are like there up 10 nanometers only. Those forces, these van der Waals forces are actually attractive forces. So these actually like these van der Waals and repulsive force will be there on these forces will be there on the surface on all type of samples, whether it's a conducting or non-conducting or magnetic or coulombic means electrical samples. Any sample if you take, these two forces will be there definitely the sample. Like as I mentioned earlier, like if your sample is magnetic, then only the magnetic force will be there. Otherwise, it will not be there. Like that. So these depends on the sample, but these two forces will be there on all type of samples. Okay. So like what like for example, if your this is your surface and surface roughness means like your these forces also like repulsive force and also forces also will follow the same way how this surface roughness is there. Like for example, this blue is a kind of repulsive forces, and this red one is like attractive forces. So those also will follow the same way how the forces are there. Okay. So now like AFM, like how it works is like assume that this is your surface. It has this kind of some step. Huh? So now like let's take like these. This is a kind of repulsive forces which is following the exactly the step of your surface. And now if I take a very short tip, actually this is a tip and this we called as a cantilever. So this sharpness of this tip will be around a few nanometers. And if I take this tip very close to this repulsive forces, what happens because of these repulsive forces, this tip will repel. It goes up. But what we do is in the AFM, we apply little bit force from tip onto the sample. So by applying a little bit force, we are entering into this repulsive force region by applying little force. So by keeping this force constant, then now we are scanning like laterally. So when it goes this sample at this place, you can see like here the repulsive forces are not there. So it will not. It is not experiencing these repulsive forces now. So, but it has to maintain this applied force initially, whatever the applied force was there, that it has to maintain constant while scanning. So that's why like what it will do is the tip will go again down. So like this, like when this tip will come at this place, what will happen? Like here, because of this wall, it will experience more repulsive forces compared to at this place. So that's why automatically tip will go up. So like this, because of the forces present on the sample and also because of this applied force, so the our tip or cantilever is following the your surface roughness. So now like we know that the tip is following our surface roughness, but we don't know like how much actually tip is moving up and down. So that we don't know. To know that one, like what we are doing is we are taking a laser and aligning at the end of the cantilever, and the reflected laser is going to the photodetector. This is a position sensitive photodetector. Means position of the reflected laser will be noted down at each pixels like while it's scanning. So now like you can see here it's almost flat. So the reflected laser is at the center. But when tip comes onto this some kind of particle or something, so tip goes up. When tip goes up, here also the reflected laser also goes up. The same way, if some pit comes in the surface means the tip goes down. Like here also the laser spot also will goes down in the photodetector. So actually, so this photodetector is telling us like how actually tip is moving while scanning laterally. So as I also told like earlier, the AFM is doing a like line by line scanning. Okay. So like this is how like for example initially it will be at the center like when it yeah. So you can see the difference like when it okay. Yeah. So like this, it goes up and down. So that photodetector. And like now, like assume that like this is some spherical feature is there in your sample. So now actually AFM is doing line by line scanning on that one. So for each line we are getting a X versus Z profile. So that like for one line we are getting this kind of X versus Z profile, like tip how it is moving. The same way, like if you combine all these line height profiles, so you get a 3D image. So if you combine all these things, like then you get a, so this kind of 3D images. So that is how it is generating an 3D image in the AFM. So it's same like touch and feel. Like you can see, like this is a Braille script. So how actually blind man read this Braille script is just like by touching the these prototype dots. He will feel these how many dots are there, and in what shape their dots are arranged. So by just the number and the arrangement, he will read this Braille script. The same way, the tip in the case of AFM, the tip will feel the forces present on the sample, and based on that, it will construct a 3D images. So as I like, this is actually a silicon substrate, this full one, and it's actually in few, like this is like 1.6 mm and this is just 3.4 mm, and the one line, one beam will be just coming from the center, and that will be extended a little bit. That we call it as a cantilever. If you see this cantilever in a SEM, it looks like this. So this is a cantilever and this is a tip. And this sharpness of this tip is will be in a few nanometers. Like generally nowadays it will be available. Minimum is available at 2 nanometers and maximum up to 50 nanometers are available. And this generally like the material will be silicon or silicon nitride will be there. And now let's see like what all we can do with an AFM. So like with an AFM, we can get a 2-dimensional images and 3-dimensional images. So like whereas in optical microscope or SEM or TEM, like you get only 2D images, but here we can get a 3D images also. And we can also like measure the surface roughness and some particle size, particle height or film thickness, like height distributions, like histograms, and like particle size analysis. So all these things we can do with an AFM. And also, like as I mentioned, like we can do whether like biological samples or conducting or non-conducting samples imaging we can do with an AFM. And one of the beauty of AFM is that actually we can do imaging in any medium. Like we can do in the air medium, we can do in the liquid medium, or we can do in the gaseous medium, or like humidity, or we can do at different temperatures, like heating, cooling. Means like we can heat the or cool the sample and see how actually the morphology is changing when you heat or cool. Like. Okay, and as I mentioned, like here, like we can do the imaging in the fluid medium, so we can do the imaging of live cells. Like in if you want to do imaging of live cells in SEM or TEM, it is very difficult because you need to SEM and TEM works under vacuum. So like once if you put your cell in the vacuum, so vacuum will absorb all your moisture or whatever the water content is there in the cell. So cell will die. So you are getting the imaging of dead cell. But whereas we can keep here in the AFM, we can do in the imaging in the fluid medium. So we can do the live cell imaging, and also we can do some kind of dynamic studies. Means like by time how the morphology is varying or something, like when you like inject some kind of drug or something to the cells, like what morphology is changing. So that kind of dynamic studies by time also we can do it with an AFM. And actually we can combine the AFM with inverted microscope or fluorescence microscopy and all. So simultaneously we can do AFM along with in a fluorescence microscopy or something like same, like kind of correlative studies we can do with an AFM. And also like we can not only we can get the surface morphology of the samples by AFM, we can also like measure some kind of surface property measurements like electrical properties, magnetic properties, mechanical properties of the surface. Like here some kind of mechanical property, mm, this one imaging we are seeing, like how actually the modulus is changing in the this kind of polymer blend, we can see it clearly. Like we can see like in the mechanical properties, like we can measure this kind of properties. For thermal, like we can measure melting point of your surface or thermal conductivity of the surface. For electrical magnetic, like current, capacitance, or surface potential, work function, so those things and all we can measure with an AFM. Like how we can measure, like we have a different type of application modes are available. So using these modes, all these different surface properties we can measure. And also we can do the nanolithography, and also like nano manipulation also we can do. So like nanolithography means like we can make some patterns, or you can write your name or image and all, we can do it on the surface. And in nano manipulation, like using a tip, we can push them, these particles, and arrange them what order you want. You can arrange them like just by using the tip, we can push them and arrange them. So that kind of nano manipulation also we can do with the AFM. So now coming to the AFM specifications, like the vertical resolution, we can go up to like zero 0.5 angstroms, and the lateral resolution, it depends on the sharpness of your probe. If your tip size is like 2 nanometer, then we can get the 2 nanometer resolution. We can go lateral resolution. In the case of HTM, actually it's 1 angstrom. We can go the lateral resolution. Scan size and all, it's depends on the actually scanners what they are using, but typically it will be like 100 micron into 100 micron into 10 micron height. And the sample size, typically we can keep kind of glass slides and all we can keep, and up to 10 thick samples we can keep. But based on the different models, we can like keep like big wafers and all, 300 big wafers, and with up to like 27 thick samples we can keep. Yeah. And now coming to the different types of modes available with an AFM. So there are actually three basic modes are there in the AFM. So one is contact mode. In the contact mode, what happens is tip is touching the sample and doing the raster scanning. So here, how actually tip is deflecting based on the surface, we are actually monitoring it. Like you can see, like this is your surface, means like initially you can see the reflected laser in the photodetector is at this place. You can see here, like when it goes to, it's still same. Like you can see here. So when it goes to this one, tip going up, like here also the reflected laser going up, and here it is going up, but it has to maintain this here. It was initially, it has to maintain here constant. So that's why like the feedback will adjust the cantilever Z height. Then again it will come back to the this position. You can see like this height it is adjusted, and now it came back to the original position. So like this, it is scanning the surface in the case of contact mode. So this is there is a small video is there. Yeah. So like this is how like some little coin, I think something. So illustrative, like this is how like line by line it is scanning. So it will be following the surface surface roughness tip. We can't do the as big as like a coin size scanning. We can't do. We can do maximum sample size is 100 micrometer only. Okay, case of this AC mode, it's called a tapping mode or semi-contact mode. In this case, like what will happen, like there is a small shake piezo is there, like we apply a little bit biasing to the this piezo, then this will start oscillating. When it start oscillating, this is attached to this cantilever, no? So cantilever will also start oscillating. So tip is oscillating and lightly tapping the surface. So now, like here also, like when this is oscillating means here also the laser spot also will be oscillating in the photodetector. Like you can see here now, this is how like it is oscillating. You can see here again. So like this is oscillation. It has to maintain this amplitude constant. But when it goes to from here to here, so now you can see when it goes to here, it is like the amplitude become very small, but it has to maintain this amplitude while scanning. So what it will do is it will adjust the again the tip height. Like you can see here, it is adjusted the tip height, and now it become, you can see again it become the amplitude bigger. Whatever it was there initially, like that amplitude it become. So like this, it is monitoring the amplitude of this oscillation, tip oscillation, and then it's giving us the images in the case of tapping mode or semi-contact mode. So it is like this. There is a small video. Oh, sorry. Yeah, you can see like this is how like tip will be oscillating and scanning on the surface. Okay, and there is another mode called non-contact mode. There is here also tip is oscillating, but here it is not touching the sample. So it is little bit above the surface and scanning the surface. And in the contact mode, tip is touching the sample and scanning it. Like in the case of contact mode is working in the repulsive force region, and here as it is touching the sample, like if we have some kind of small water layer on the sample, as actually AFM we are doing in the ambient conditions, sometimes like because of the humidity, a very small amount of water layer may be there on the sample. But here in contact mode, as it is just it is touching the sample, it will go inside this water layer and scan the surface, so you get a same height, correct the surface morphology you will get it. In the case of tapping mode also, it is oscillating and tapping the surface. So here also it goes inside the water layer and then gives us the correct image. Whereas in case of non-contact mode, it will be not touching the sample, it will be little bit above the sample it is maintaining. So if we have some kind of water layer on the surface, so we are actually getting the image of water layer. Okay, so not the surface actually. So so that is one drawback of this non-contact mode, and so that's why like people use mostly tapping mode and contact mode, and this non-contact mode is very good in the case of if you're doing in a vacuum. So that was these are the main basic modes of the AFM. Okay, and now coming to the how to prepare the sample. Like as I told, like our actually AFM, it can take up to 10 mm thick samples. If your sample is solid sample and it's within a 10 mm thick sample, then you can keep the sample directly. But if your sample is very big and all, you need to do the cross sectioning or cutting or microtoming, or you can use the FIB and all. And also, as I mentioned earlier, like maximum 10 micrometer surface heights only it can measure, not more than that. So if your sample is too rough and all, you may need to do polish it. You have to do polishing, and then you need to do imaging in the AFM. And also, if your sample is powder samples, then what you need to do is just take a very small amount of sample and dissolve or disperse in any solvent, and then sonicate it for some time, and then take a drop of that one and put it on any flat substrates. So I'll tell you what kind of flat substrates we can use. Or you can do the spin coating, or you can do the CVD, PVD, and sol gel technique and all. And then after that, you can dry that one and then use it for the imaging purpose. So these are the atomically flat substrates. This kind of flat substrates we can use because the roughness of these substrates are like in angstrom level. So so that's why like these substrates are better, like mica or glass slides or HOPG or silicon oxide wafers, and all are good for the sample, for the powder sample preparations. And like if your samples are like biological samples and all, like for example, if your sample is protein, then graphite is actually good substrate. If you want to do some pulling experiments and all, like gold substrates are good. And for cells and all, like you can use like cover slip or petri dish or glass slides are all good. And sometimes like some biological samples, you need a small amount of preparation. Like for example, if you want to do the DNA imaging, then as you know that DNA is negatively charged, And like for DNA, mica is good substrate, and mica also is also negatively charged substrate. Surface is negatively charged actually. So what we need to do is we need to, like, if you put the DNA on this mica, as both are negatively charged, so the addition between the DNA and mica will not be good. So when you are scanning, these DNAs may move. So we need to fix these DNAs on the mica. Then only we may get good imaging. To do that one, like what we need to do is like we can use some kind of this kind of APTS solvent to functionize the mica, or you can do some kind of salts you can use on the mica, so that like your mica will become positively charged. And then after that you put a DNA drop on the mica. Then as now your surface is mica surface is positively charged and DNA is negatively charged, so addition between the DNA and mica will be good. So now when you are scanning, these DNAs will not move, so you get a good imaging. So like this kind of some small preparation will be required for sometimes for biological samples. And like what all accessories we can use, like you can use metal disc. This is some steel disc, or you can use even glass slide or cover slip also. On top of that, you need to put a kind of some double-sided tape. Like this is a black one, you can see that is a double-sided tape. On that one, they put a sample. So now you can take this one and use it for the AFM imaging. If you are doing some kind of electrical measurements, as I mentioned, like you want to do some conductivity property measurements and or something, so that time, like instead of using this non-conducting tapes, you can use some conducting tapes like copper tape or silver paste and all. You can use it instead of this non-conducting tape. Coming to now about our Oxford AFMs, like mainly like we have three different types of models are available. So this is we call it Cipher, and it's a very high resolution AFM and very fast scanning AFM. Like we can do in a video rate scanning, we can do with this kind of Cipher, and this is mainly for the semiconducting industry and all. Like here we can keep the kind of 300 big samples we can keep here. And this is a kind of small like up to 80 samples we can keep, and this is a kind of basic research grade AFM. So this is how actually it looks. So this is a anti-vibration table. So whatever the floor vibrations will be there, no, so that will not go to, that will not reach to the AFM because of this anti-vibration table with a granite base. And now this is the acoustic enclosure, like whatever the acoustic noise will come, so that will avoid this acoustic enclosure. So this is our actually MFD 3D Origin Plus system. Yeah. So this is a controller, and these two monitors and PC will be there. And with our AFM, like we supply these many modes as a standard modes, and these will be optional modes, like one can add at any time actually. And like this is our partial Indian users list. Like we have our AFMs in all like IITs, ISERs, or different like CSIR or DHT labs and all, or universities and all. So now coming to like traditional AFM versus our AFM. So like in the market, actually there are two different types of scanners are available. So this is a scanner. Here we keep a sample, and your scanner will move in X, Y, and G. So here it's a tube scanner. Like you can see, it's a tube type is low. So tube scanner. Here like bottom end is fixed and top end is moving. So as this one is fixed, so when it is moving, because of this, you'll get some kind of bow in the image. So this kind of bow you may get. But whereas like here, these are like flexure based scanners, so it's not kind of tube based. So you get a almost flat images you can get. So here, like you can see, your surface is actually flat, but you are getting some kind of bow because of this scanner design. And actually, all our AFMs are this kind of designs. And also like all these scanners are all actually made up of piezoelectric materials. So piezoelectric materials are kind of like, that they have a kind of hysteresis will be there. Like hysteresis means like when if you apply some kind of voltage, initially it may go like this. When it is coming back, it may come in different path, but it has to come on the same path. No, but it will not come. It will come in a different path. That is called hysteresis. So that kind of thing will be there in the case of all these piezoelectric materials. So because of that, if you are doing FD curves, you get this kind of differences. Or you can see here at the center it will be nice, but at the end it will be your images will be stretched and all. And if you're doing lithography and all, if you draw a circle, you'll not get a circle. But whereas here in the closed loop scanner means what we are doing is to this piezo scanners, we are attaching LVDT sensor. So that LVDT sensor will tell that how much actually a difference is the scanner is moving. So that this LVDT will sense that difference and apply extra for voltage so that it will come back to the original position. So because of that, like you get a good force curves and very good images at the center and at the end also. And if in the lithography also, if you draw a circle, you get a circle like that. So that all our actually scanners are like closed loop scanners. And also we use like SLD lasers, whereas like many other traditional AFMs, they use a normal visible light laser, but whereas we use a IR SLD laser. So because of that, like what happens, like when you align the laser at the end of the cantilever, some small amount of sample laser will be falling on the sample also. So the reflected laser from the cantilever and the reflected laser from the so from the sample both goes to the photodetector, and their interference will happen. Interference patterns will come. So like if you are doing FT curves, you will get some this kind of patterns in the FT curve, whereas in the SLD you won't get. And even like if you are doing in the imaging also, you get this kind of interference patterns if you are using a like red laser and all, visible lasers. But whereas in the IR SLD laser, you don't get this kind of fringes. And all our actually in our Oxford AFM, so we provide SLD lasers only. And also one of the disadvantage of this visible red laser is that like if you are doing a kind of inverted AFM with inverted microscope, this is a kind of some cells and all. So you added some fluorophores to see them clearly in the fluorescence microscopy. But these red laser, so these cells will absorb these red lasers. Means like whatever the fluorophores you add, so that will absorb these red lasers. So you won't get any fluorescence images in the fluorescence microscopy. So you can't recognize these cells. But whereas this SLD lasers will be little bit above like around 850 nanometers. So this kind of problems you don't face with an Asylum research AFMs. So that's about like traditional AFM versus say Asylum AFM. So now like coming to different application modes. Like as I told, like you can do along with the surface morphology, we can do some kind of property measurements. So one is like magnetic forces. Like if you have a like for example videotape, if you see, so there are some magnetic domains are there. Like if you take a hard drive also, like the different types of like magnetic domains will be there. So that if you want to see, so you have to do a MFM, magnetic force microscopy. Here what we do is instead of silicon tip, we take a magnetic coated silicon tip. So this is coated with some magnetic material. And these are the domains, like they are oriented in different direction. So what we do is we take this magnetic tip and we magnetize that tip. When you magnetize, there are some like you'll get some kind of orientations, whether it is upward or downwards. So now watching that this is like this kind of orientations are there. So when tip comes at this place, so because like here this one will attract your tip, so tip will go down. So when tip goes down, you'll get a dark contrast in the image. So with the same way, when tip goes at this surface, you can see here both will repel. So tip goes up. It will, as tip repels, so tip goes up. So when it goes up, like you'll see the bright spot in the image. So these bright and dark spots in the image gives us the idea that those domains are oriented opposite direction. So this kind of magnetic domain information you can get with the magnetic force microscopy. The same way, like if you want to do it, actually this magnetic force microscopy at different external magnetic field, like you can see this is a some external magnetic field, this is a sample. So actually these two are kind of magnets. In between the magnets we are keeping some sample, and we are applying different external magnetic field to the sample. So because of this external magnetic field, so you can see like how your magnetic domains are changing. Like you can see this is a, like you can see like at the different external magnetic field, this domains are a little bit changing. So that kind of studies we can do under different external magnetic field. So we can actually apply external magnetic field up to 8,000 Gauss in plane, and out of plane you can apply up to 1,500 we have. Okay, and now in the case of like electrostatic force microscopy, we can find if you have any static charges on the sample. Like for example, like you have positive charge and negative charge on the sample. Here, like what we do is we take some kind of any conducting coated tips, any gold coated silicon tips or platinum coated silicon tips we take, and we apply a little bit biasing to the tip. When you apply some positive biasing, so it will be positively charged. And here, when it comes to this tip, when it comes to this region, positively charged domain region, so because of this positive, so tip will repel. So you get some bright spot in the image. When tip comes at this region, here your sample will attract the tip. So tip goes down. So there you get a dark contrast. Like that, we can get some, like this is actually morphology image. And you can see these are the some kind of static charges are there. So this kind of static charges studies we can do with an EFM. And this is one of the example, like some conducting nanoparticles are embedded inside the this sample. Like you can see this is a morphology, and this is some kind of normal amplitude and phase image. We can see, we cannot see any like these embedded nanoparticles inside this one. Those are conducting actually. With an EFM, we can see like where those embedded nanoparticles are available, that we can see with this electrostatic force microscopy. And in the case of Kelvin probe force microscopy, we can find out the work function or surface polarization or surface potential of the sample. Like for example, you can see here, this is some silver, gold, some silver, different type of metals are there. So we can find out the work function of this material. So like 4.55 is for My. That is the work function of this material. Like that, we can find out the surface potential or work function of the sample. We can find out with the KPFM. So like same way in the case of conducting AFM, here also we take a conducting tip, and we here in this place, in this case, like we are doing imaging in contact mode. I mean, tip will be touching. So when you apply biasing to the tip, so if you have a conducting region here, so current will pass through this region. If you have a non-conducting region, current will not pass. So like this, you get some bright and dark spots in the image. So you can see this is a topography image, 3D image of the carbon nanotube. So you can see lightly, but whereas in the conducting image, like you can see clearly, because here current is passing through, so you can see those conducting means nanowaves. You can see very clearly. So, and also we can do the IV curves also, like this is some ZNO doped with U. So like wherever, like if you want to do IV curve on that, exactly on this spot, you can do IV curve. Like you can see like 3 different IV curves at these spots we did. So like this, we can measure the your conductivity properties on these particles, nanoparticles and all. And also, like if your sample is generating any kind of photocurrent, because as we are using some laser, so some small amount of laser may fall onto the sample, so that may generate some kind of photocurrent in the image. So you want to avoid that one. Like we have eclipse mode. In the eclipse mode, what it will do is initially it will do one scanning with the laser on. So that time laser will be on. And then you get a surface morphology, and after that the same line will scan one more time to avoid this photo current. That time this laser will be off. So like this, it will do the same line 2 times scanning, and then one time it will do topography, and another time it will do, by switching off the laser, the current image. So like this, you can see this is with the laser on, we can see some photo current. This is with the laser off, we can see very small amount of current at this place only, not at these areas. Like this, we can do some, we can avoid a photo currents and all in the image. And also, like if you want to do not only this just IV curve, if you want to do like 2 probe or 3 probe conductivity measurements by keeping extra two this kind of titanium probes, like this is one titanium probe and this is a AFM tip. So we are doing so like 2 probe conductivity measurements we can do. So this kind of probe stations are also available with us. And also in the case of piezo force microscopy, like we can do like this kind of samples like ferroelectric materials or actuators, transducers and all. So these are like actually piezo materials. So if you have any kind of what do you call piezo domains and all, like we can do like both vertical and lateral domains. We can we can do imaging with this piezo force microscopy. So we have like some samples in the piezoelectric material, it needs a higher voltage, whereas with a normal any AFMs, we can apply only 10 volts to the sample. But whereas with a high voltage setup, we can go up to 220 volts. So some samples and all, like for example, PPLN, that kind of samples will be require higher voltages. So we have a higher voltage setups also. And now coming to like nanomechanical properties is like if you want to measure, like as I told, modulus or adhesion or like some loss tangent. So that kind of mechanical properties is if you want to measure on the of the surface, then we have a different types of modes are available, and a few I will explain. Like some like for example, this force modulation can measure the modulus from in this range only, whereas AMFM we can measure from here to here in this range modulus it can measure. Like that, different techniques are there, so those will be good for different types of moduluses and all. So in the case of like force curves or force maps, like what we do is we take a tip and we little bit apply force onto the sample, and with that one like how actually tip is deflecting or bending, based on that one, so we can calculate the modulus of the samples. Okay, so some electrostatic modulus we can calculate. And in the multi-frequency AFM, this is called AM/FM mode. So what we do is, like you can see, this is a cantilever movement. Like you can see, so this is how it cantilever will be oscillating. So if you sweep cantilever with the different frequencies, so you can see actually like this is the first frequency and this is a blue one is second one, and the total because with these two, the combined oscillation will be this one, what you call the brown one. So this is how it will be oscillating and tapping the surface. So with that, what we can get is like with that we can measure the kind of stiffness or elasticity or like dissipation, like how the energy is lost in the sample when doing this one, or kind of loss tangent of the material and all we can measure with this AM FM viscoelastic mapping. Like this is the one kind of packaging material. You can see like there are different types of polymers are available, so we don't know like what is which one is what polymer and all. By doing this AM/FM mode, like you can get this kind of imaging. With this imaging, like it is telling that this modulus of at this place is different, and here is different, here is different, here is different, like that. So with that modulus, like as we know, like these polymers, so by literature we can find out the modulus of this P, T, P, and all. Then we can match with that whatever the modulus we got it from this AFM FM, and then we can identify which one is what material and all. So this kind of mechanical property measurements we can do for like for packaging materials and all, or polymers, different polymers and all. And with this indentation, what we are doing is we are taking a diamond tip and we are indenting onto the tip. By applying more force, we are actually a little bit indenting onto the sample. and like what force you are applying and how much area you indented. With that, actually, we can calculate the hardness of the sample. Huh? So like that, we can calculate the hardness. So that also possible with an FM. And this is I think my last slide. So here, like some kind of stress and strain measurements, if you want to do with AFM, that is also possible. Like you can see, this is one. I think some polymer are there. These we using these things. We are actually stretching the this sample, and after that, like when it's stretched at whatever the force, at that place we can do the imaging, like again apply a little bit more stress and then do imaging. So like that, stress and strain measurements we can do on the sample. So this is a latex sample. Like you can see how actually this some kind of breaking is happening in this kind of sample. Like you can see, it's at this place, I think some you can see like here. Mm. So this kind of stress and strain measurements are also possible with an, our instruments. And maximum force we can apply is up to only 89 newtons we can apply with this one. Okay, thank you for your attention. Like if you have any doubts and all, like you can ask.
Thank you, sir. Sir, shall we go with the question and answer session, sir?
Yeah, sir.
Hi, sir. Dear participants, if you are having any questions, please unmute yourself and you can ask directly to our resource person. He is ready to answer for your questions. Or you can type your question in the chat box. We will ask on behalf of you.
Yeah, that is also possible.
In chat box, we are receiving overwhelming positive responses, sir. It is excellent session, sir. Thank you.
Oh, thank you, sir.
Hello.
Thank you.
Hello.
Yeah, sir.
Sir. Yes, sir.
Very good lecture, sir.
Oh, thank you, sir. Thank you very much.
Actually, that about liquid solution, can we
Yeah, sir.
use that AFM in a high pH liquid solution?
Sir, actually, liquid, that is a liquid imaging, means like your sample will be solid sample only, but we are keeping in the liquid medium. We are doing in the liquid medium only. And you can actually do at a different pH also we can do. As I mentioned here, like you can do at a different pH, different humidity or different temperatures, and all are possible. So actually we use what you call it, I think PTT kind of material, so that like that will be compatible to almost all different types of chemicals or solvents or different pH material and all. So nothing will happen. Like you can do a different pH also. Yeah.
Okay. Thank you.
Yeah.
Another one, that time duration you mentioned in your last slide. Can you take, I think, after 30 minutes or 1 hour interval?
Yes, sir. Like this is what like dynamic studies we can do. So like sometimes what we do is like as I told, this cell. So this we kept cell and we inject some drug onto that one. So now like how actually this cell's morphology is changing when actually it is reacting with a drug. So at different timing, like after 5 minutes, after 10 minutes, like that at in situ measurements, dynamic studies we can do. That is possible.
Okay. Thank you. Another thing is that if you use biological sample,
Yes, sir.
any, I think there is some problem happened to this machine AFM, like toxic.
No, sir. Nothing will happen here.
Okay. Thank
No,
you.
no, sir.
Okay. Thank you very much.
Thank you, sir. Another question in chat box. Shall I read it, sir?
Yeah, it's okay, sir. I will read it. No problem.
Please share any software to analysis AFM images or any free softwares available.
Yes, sir. There is one software called Guardian. So this spelling. Okay, let me type it here. This is like one free software available in the internet. I think you can see with this screen, no?
We are
Hello?
seeing. Yes, sir. Yes, sir.
Yeah, this the Google screen you can see. No? So
Yes,
this
sir.
Guardian, this is a free AFM software. You can use it, and also like generally whichever AFM you buy, along with that one software they will provide from their own software they will provide. If you don't have this one, like this is a one free software available in the internet. You can use this one. Guardian it is. Okay.
Thank you, sir. Dear participants, if you are having any question, you please ask. You can
Sir,
unmute
good morning,
yourself.
sir.
Yes, sir. Please, sir. Proceed, sir.
Myself, Rajesh from SVC, sir.
Yes, sir.
Sir, actually, in case of SEM analysis, sir, we will be getting the composites count. For example, what are the different composition that has been involved in the composite material?
Yes, sir.
Like
Yes,
that,
sir.
can we able to take in AFM also, sir, like EDAX test?
No, sir. Here you can't do it like that. You won't get any
So we
elemental
cannot able to
elemental
separate.
analysis and all
Like
it.
that. Yeah, sir. Elemental count, can we able to get in this, sir?
No, sir. No, sir. Here it's not possible, sir.
Okay. Thank you, sir. Thank you, sir.
Yeah, yeah.
Thank you, sir.
Yeah. Welcome, sir. I will show
Dear,
my screen, sir.
yes, sir. Yes, sir. Sir, shall I go with vote of thanks, sir?
Madhivanan, sir.
Yes, sir.
If you don't have any questions, participants who
Yes.
don't have any questions, they go ahead with the vote of thanks.
Okay, sir. Thank you, sir. Thank you, sir. Thank you. Thank you for your wonderful presentation, sir. Your presentation added more value for this short-term training program. Really, it is excellent presentation, sir. You have given a good knowledge about atomic force microscope, which are useful for all the participants. The takeaway your presentation from your presentations are very high. We have started with the scanning probe microscope family, atomic force measurement and force interaction, force and their range of influence, how it works, image generation, and what can AFM can be used for, like live cell various properties, and AFM specification, imaging contact mode, basic mode of AFM, and atomically flat substrates, biological samples, assessments required for AFM, ASLM product lines, and MFD 3D origin equipment, and comparison of traditional AFM and ASLM AFM, and variable field model, and electrostatic force microscopy, Kelvin probe force microscopy, and conductive AFM images, and nanomechanical properties, multi-frequency AFM, AM, FM viscoelastic mapping, finally nano indentation and stretch stage. It is a very really excellent presentation, sir. Thank you very much, sir. Thank you, sir.
Thank you, sir. Thank you very much again.
Sir, good morning, sir. This is Chandrasekhar Reddy, so convener of this program.
Yes, sir.
So on behalf of management, Principal Department of Mechanical Engineering of SVCE, and
Yes.
participants of STTP, thank you very much for accepting our invitation and delivering an informative and thought-provoking webinar on recent advances in atomic force microscopy by Oxford Instruments, organized by SV College of Engineering, Tirupati, in spite of your busy schedule. Thank you very much, sir. Thank you very much.
Thank you, sir. Thank you very much.
Thank you, Basara, sir.
Thank you, sir.
Madhivanan, sir.
Yes, sir. Yes, sir.
I think sir is available. One or two we have to remove. We have to go out and you have to see in the YouTube, I think, sir.
Okay, sir. Okay, sir. I will
Because
request.
sir is not able to. So ask our faculty to.
Yes, sir. I will ask. Sure.
YouTube, because it is yes. Sir came, I think so.
Okay, sir. Okay, sir.
Yes. Now, sir can join now. Just I will ask.
Yes, sir.
Keep second slide, Rajesh.
Professor,
Welcome, sir.
yes,
Welcome,
sir.
Pandian sir. Welcome, Pandian sir. This is Chandrasekhar Reddy.
Hi, hi, hi. Can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Just wait, sir. We'll go to introduction about you, and then afterwards we'll go ahead with the presentation, sir.
Okay,
Uh,
fine.
uh,
Madhyanan, sir, take
sir,
over.
I will start. Okay, sir. Thank you, sir. Thank you, sir. Now, let me introduce our resource person, Dr. K.K. Soundarpandian, sir, scientist from Government of India, New Delhi. He is currently serving as scientist for Government of India in Ministry of Electronics and Information Technology, Office of CCA, New Delhi since 2018, with the responsibility to handle the digital signature certification, PKI, and Internet of Things. He had been served as research scientist grade 1 in Indian Institute of Information and Technology, Design and Manufacturing, Jabalpur for 12 years and executed the research work in the field of VLSI, cryptography, PKI, etc. He had been served as research scientist grade 2 in Indian Institute of Technology, Kanpur for 5 years and executed the research project related to mechatronics and robotics. He worked as a project engineer for 2 years and executed to develop IP core and FPGA board in Center for Electronics and Design and Technology of India, Ministry of Communication and Information Technology. He had guided many doctoral research scholars for their research work, and one of his research scholars have received Young Scientist Award under his guidance. He had published more than 40 research articles in SCI index journals and conferences. He had completed 3 funded and consultancy projects as a principal and co-investigator. He had obtained 5 patents for the benefit of society. He had received Outstanding Scientist Award for his contribution towards research excellence and accomplishment in the area of electronics and communication. We welcome you, sir. We are honored with your presence, sir. The current session topic is impact of emerging technologies and the challenges for promotion of manufacturing and implementation on Internet of Things. Now, I request our resource person, sir, to proceed with the session, sir. Requesting, sir.
Hi, good morning to all.
Uh,
I'd like to thank
Sir.
everyone and
yes, sir. Yes, sir. Yes, sir. You can share your presentation, sir. Yes, sir.
yeah. Okay. I'm getting the document.
Pandian, sir, any help from our side, sir?
I'm sharing the PPT.
Yes, sir. Sir Rajesh, Dr. Rajesh, please help,
Sir, I'm available, sir. Yes, sir. Yes, sir. Sir, Pandian, sir, I think
Yeah.
you can able to see the present now screen on your desktop. Yes, sir, in the Google Meets.
Okay.
You please press that present now, then you go the option, a window option.
Okay.
Then you have to, before selecting that, you please open your PPT on the background, sir.
Okay.
You select that PPT in that window you have got as a pop-up.
Okay. Yeah.
Then you can press the share icon, share button. Yes, sir, it is presenting. Yes.
It's available now. Yeah.
Now it is available. We
yes,
can
sir,
see,
yes.
and we can go for presentation mode.
Presentation mode, it is better, sir.
Yeah. It's okay now. Is it clear?
Yes, sir. Yes, sir. Perfect, sir. Perfect, sir.
See, good morning to all of you. As far as the topic is concerned, it's a little bit outward. The topic what you're expressing is that nanotechnology. When we talk about the nanotechnology, it is also a part of the emerging technology where IoT is going to play the role for the industrial revolution. So in this presentation, I'll be giving my brief idea about how the emerging technology is going to play the role as for the Internet of Things and how the industrial revolution has happened. as well as I'll be explaining about what are the projects